So now we understand how to add two vectors and how to multiply a vector by a scalar in one dimension. And we understand that both from the algebra point of view and from the geometry point of view. Let's go on to 2D, where this really starts to get pretty interesting. So in 2D, and let's put the algebra over here, and let's put the geometry over here. And let's first ask, what about addition of vectors? Well, we already mentioned that how to add sharks and tuna, and I will just remind you that abstractly, if we have one vector, which is x1, y1, and we have another vector, which is x2, y2, then the sum of those two vectors is the vector x1 plus x2, comma, y1 plus y2. So what does that look like geometrically? Well, let's start with our xy space, and I'm going to draw only the positive here for convenience. Let's look at our xy space, and let's draw those two vectors. So let's say here is the vector x1, y1, and here is the vector x2, y2. What is the equivalent of adding these? Well, it's just like we said here. We add the x components and we add the y components. So here is x1 right here on the x-axis, and here is x2 right here on the x-axis. And therefore, x1 plus x2, we simply take the x2 vector and we move it over to add it onto x1, and that is the sum of the two x components. Similarly, we take y1 here on the y-axis and y2 here on the y-axis, and we add these two vectors by taking y1 and adding it onto y2, and now we get the sum of those two. And this is the sum of these two, and then we simply draw the perpendicular, and we can say that the sum of these two vectors is this red vector, and that red vector is going to be x1 plus x2, comma, y1 plus y2. How did we get this? We got this by adding the components. But here's another way to get the same thing. You see what we just did by adding the x vectors and adding the y vectors is equivalent to taking this x2 vector here and just moving it over and adding it onto the x1 vector tip to tail. And so this sum of the two vectors is now represented by this sum, which we have created by moving the two vectors and placing the second vector tip to tail with the first. Obviously, addition is commutative. We could have done the same thing the other way. We could have taken this first vector and added it onto the second by sliding it over and putting it on the first one tip to tail. So that's how we add two vectors. What about scalar multiplication? Well, as we saw algebraically, a times x1, y1 is equal to ax1, comma, ay1. And geometrically, what that amounts to is, again, taking the xy axis and taking our vector x1, y1. If a is greater than 1, then a times x1 is going to be a longer a factor of a longer than x1. So here a is about 1.5 because this is about 150% the length of the original. And this value is, of course, ax, ay. So multiplying a vector by a scalar is just stretching it out in the same direction by amount equal to the value of the scalar. And so that is the geometry of vector addition and scalar multiplication. And in 3 dimensions, or as we'll see later, in 4 dimensions or 12 dimensions, it's really working the same way. You add vectors by placing them tip to tail, and you multiply a vector by a scalar by extending it or contracting it according to the value of the scalar. And that's true in all dimensions. By the way, we were saying that if you take a vector, let's say a 2-dimensional vector in the xy plane, and you multiply it by a scalar, a, that if a is greater than 1, then multiplication by a acts as a stretcher, and this is a times the vector. And if, on the other hand, a is less than 1, then it acts as a shrinker, and the resultant vector is shorter. We did not deal in this case with negative scalars. And of course, in many of our cases, the xy planes have to be positive or 0 only, because in quantities like sharks and tuna, negative quantities don't make sense. But in general, they do. And we have to think about the full xy plane with both positive and negative values. And then here is our vector. And now we want to talk about, what about scalars that are negative? For example, what about a equals minus 1.5? Well, let's think about it. If we take a vector in the xy plane, let's say the vector 5, 6, which is that point right there, and we draw the vector, and then we want to multiply this vector by minus 1.5. So minus 1.5 times 5, 6. We know how to do that. That's equal to minus 7.5, comma, minus 9. So the resulting multiplication of the scalar by the vector produces another vector in the negative direction, where this is minus 7.5 and this is minus 9, and this is the vector that is minus 1.5 times the green vector. And so multiplication by a negative scalar flips a vector because it multiplies its components by negative numbers